Hello friends. So today we are going to second session of kinematics of machines. So earlier we were discussing about velocity and acceleration analysis methods. That too we were learning about one of the type of graphical method, that is relative velocity method. So I am going to continue with the same today, and in this session we are going to learn about what is meant by velocity of rubbing, and we are going to solve one problem again based on relative velocity method, but this problem is of slider crank mechanism. So let us begin with what is meant by velocity. So velocity of rubbing means, let us consider the two links which are joined like this. So this is the turning pair which consists of a pin and hole arrangement, and these two links are connected by this pin and hole arrangement so that they can rotate about this pin. So velocity of rubbing is nothing but an algebraic sum between angular velocities of two links which are connected by pin joints multiplied by pin radius. So the product of the algebraic sum of these two angular velocities omega 1 and omega 2 multiplied by the radius of this pin which is connecting these two links is called as velocity of rubbing. So rubbing velocity at point O is given as omega 1 minus omega 2 into r if the links are rotating in same direction, and it is omega 1 plus omega 2 into r if the links are rotating in opposite direction. Please see here, if they are rotating in same direction, I mean if the both are rotating in clockwise direction only or both are rotating in anti-clockwise direction only, then we have to take the difference between them, multiply it by radius, and if both are rotating in opposite direction, then the summation of angular velocities of those two links multiplied by radius. So here omega and 1 and omega 2 stands for angular velocities of link 1 and link 2 respectively, and r is radius of pin joint. So this is what is meant by velocity of rubbing. Now let us solve a problem based on slider crank mechanism. So this is a IC engine mechanism which consists of a crank AB, connecting rod BP, and slider P. And here the crank AB length is given, which is 0.5 meter, and the connecting rod BP length is given to you, which is 2 meter long, and the angle of orientation of this AB is also given to you, which is 45 degree, and the rotational speed of this crank AB is given to you, which is 600 rotations per minute. And it has been mentioned in the problem statement that the crank is turned 45 degree from IDC. So these are the two terminals of this crank. One is IDC, another one is ODC. IDC means inner dead center, ODC means outer dead center. So this crank is making an angle of 45 degree from IDC, inner dead center. So in this problem what has been asked is you need to determine how much is the velocity of this piston in meter per second, how much is the angular velocity of this connecting rod in radians per second, and there is one point in on this connecting rod D which is at a distance of 0.5 meter from B. So what will be the velocity at this point D with respect to fixed point A, that you have to determine, and acceleration of the same point also you need to give, and you have to calculate the angular acceleration of this link or this connecting rod BP, and at the end we have to calculate the rubbing velocity of all these pin joints. What is the rubbing velocity of pin A, pin B, and pin P? So that's what is the problem which has been given. Let us solve this problem. As I already mentioned, relative velocity method consists of three steps. One is drawing configuration diagram, then second one is velocity diagram, and the third one is acceleration diagram. So for configuration diagram, here is the reference, a rough diagram which I need to convert it into actual scale. So first thing is draw horizontal reference line, and before that, I'm sorry, I have to select an appropriate scale. If you have, we already read the problem statement wherein the crank length AB is mentioned as 0.5 meter and the BP, the connecting rod length is of 2 meter. So the scale which I am selecting here is 1 centimeter is equal to 0.5 meter. That means if AB crank is of 0.5 meter, that I am going to draw with a scale of 1 centimeter. And if BP, if you consider it is of 2 meter, that means I am going to draw it to the scale of 4 centimeter in this diagram. So first draw a horizontal line, a reference line like this. Then locate any arbitrary point on this, place the protractor, measure an angle of 45 degree and draw a line of 1 centimeter like this. So this is link AB which is inclined at 45 degree and its length is 1 centimeter to our scale, and in actual scale it is of length 0.5 meter. Next I need to draw the connecting rod BP and its length is 2 meter, which I, when reduced to my scale, it is of 4 centimeter. So I need to use divider, place it on B, measure a length of 4 centimeter and draw an arc of length 4 centimeter, and it will coincide with this horizontal line, and that point of intersection is nothing but point P. So I have drawn an arc of length 4 centimeter, and this point of coincidence is nothing but point P. So I have completed the configuration diagram. One more thing which has been left here is I need to locate point D, and in problem statement it has been mentioned that point D is at a distance of 0.5 meter from point B, and in our scale 1 centimeter means 0.5 meter. So measure a length of 1 centimeter along PB and locate point D like this. So this is point D. So that's about configuration diagram. We are done with configuration diagram. Next we need to go to velocity diagram. So before drawing velocity diagram, let us look into the data which has been given related to velocity diagram. So in the problem statement, it has been mentioned that the rotational speed of crank AB, I mean this crank AB is rotating with a speed of 600 rpm in clockwise direction. So first I will calculate the angular speed of this link AB, and if the rotational speed is given, this is the formula which we need to use to calculate its angular velocity. Angular velocity is given as 2 pi n upon 60, and angular speed comes as 62.831 for this case, and the direction is clockwise. AB is rotating in clockwise direction. So I got angular velocity. The next thing what I do is I will calculate the tangential velocity of point B. This point B, the tangential velocity of this point B with respect to link AB, and that is given as VAB is equal to the length of this link AB multiplied by angular velocity of link AB, which we already calculated. So that comes as 31.41 meter per second. Well, this is the starting point to draw velocity diagram. So I know the magnitude of this vector 31.41 meter per second, and I know the direction in which this vector acts. This vector acts perpendicular to link AB. So I have to draw a line perpendicular to this. On that I have to mark a vector VAB. But before that I have to select an appropriate scale. So seeing the magnitude of this vector, what I have decided is I will consider 1 centimeter is equal to 10 meter per second. So 31.41 meter per second will be equal to 3.1 centimeter, nearly around 3.1 centimeter. So I will draw a line, a reference line perpendicular to AB first. On that I will mark a line of length 3.1 meter centimeter, which represents vector VAB like this. So this is the reference line which I have drawn perpendicular to link AB. On that I will select two arbitrary points, and the distance between these two points is 3.1 centimeter. Now see the direction of this vector, as I told, AB is rotating in clockwise direction. So if AB is rotating in clockwise direction, point B moves in upward direction. So that's why I have selected this point as A and this as point B, and the arrow I have shown like this. So this is vector AB. Now the remaining thing is, for remaining two links I need to draw the direction of their tangential velocity. If you consider link BP, again point B, the tangential velocity of point B with respect to link BP will be perpendicular to link BP, and piston is moving in horizontal direction only. So the uh, direction of this velocity of this piston will be horizontal. So I will draw two lines. One is a line which is perpendicular to link BP or connecting rod. Another one is a line which shows the direction of velocity of link P or slider, like this. So I have drawn a reference line which is perpendicular to link BP, and this line represents the direction of tangential velocity of point B with respect to link BP. And for slider P, as I know this slider moves on a horizontal direction only, so that's what I have drawn. I have drawn a line from point A which is horizontal. Now complete the velocity polygon. So when this crank moves in a counterclockwise direction, P comes near point A. So that's why I have shown vector AP like this, and I am measuring the velocity of point B with respect to P. So that's why vector is shown like this. Now the next thing which has been asked in the problem statement is, how much is the angular velocity of link BP? To calculate the angular velocity of link BP, what I need to know is how much is the linear or tangential velocity of vector VP. So measure the length of this edge, and when you measure it, it will come as 2.2 centimeter, and then you convert it into actual scale. So VBP is 22.2 meters per second. So if I know the tangential velocity, I can calculate the angular velocity of link BP easily, because I have this formula: velocity is equal to radius into angular velocity. What I want is angular velocity, and obviously it will be the ratio of tangential velocity to the length of that particular link. So that's what I have done. I want to calculate angular velocity of link BP. So that's why I have measured the length of this BP and divided it by radius. So it comes as 11.1 radians per second. The VBP value is 22.2. RBP value we already have the length of link BP as 2. So the ratio of this is 11.1 radians per second. So that's what is the second thing which has been asked in the problem statement. I'm sorry, that's what is the first thing which has been asked in the problem statement. The second question which has been asked in the problem statement is, you need to find out the velocity of point slider P. So that slider P velocity is nothing but vector AP. Measure it, multiply it by scale, you will get the answer. So it is coming around 2.64 centimeter. When you convert it to actual scale, the velocity of slider is 26.4 meters per second. So this is the second answer. Next, the thing which has been asked in the problem statement is, for this point D, you need to calculate the velocity. So we need to locate this point D in velocity diagram first. So again the same rule. Measure BP upon BD in configuration diagram. Take the ratio of BP upon BD. So this BP upon BD should be similar to the BP upon BD here. So calculate the BD value here in velocity diagram. BD is equal to the ratio of these two multiplied by the length of this vector. So that will give you BD. Locate that point and draw the vector AD. So this vector AD is nothing but the velocity of point D with respect to point A, the linear velocity of point D. So that I have calculated. The length is around 2.88 centimeter. Multiply it by the scale which we have. So the answer is 28.8 meters per second. So this is the third question which has been answered in the problem statement. Now the next thing which has been asked is related to acceleration, for which we have to draw an acceleration diagram. So to draw an acceleration diagram, I am going to use the table where I can easily represent both the component of acceleration, I mean radial and tangential components of acceleration, and then it will be helpful for me to draw the acceleration polygon. So look at this table. There are three links or three lines. One is link AB, that is crank. Another one is link BP, that is connecting rod. And the last one is slider, which is also one link. That what I have considered. Then in second column I have written the length of each of this link. AB is of 0.5 meter, BP is of 2 meter, and slider has got no any length. It is a small element and length doesn't matter here, so that's why I haven't mentioned the slider length. So obviously velocity, if you check, we already calculated the velocity of AB is 31.41, that's what I have written. Velocity of BP is 22.2, that's what I have written. And velocity of AP is, that means the slider velocity is 26.4, that's what I have written here. Now acceleration, as I told, it has got two mutually perpendicular components. One is called radial component, another one is called tangential component. Radial component is ratio of velocity square divided by r, I mean this column square divided by r. That's what I have calculated here. For first one it comes as 1973, for second one it comes as 246.42, for third one it will be 0 because the radius is 0. So the tangential velocity is given as r alpha, but for AB it will be 0. Why it is 0 means the crank AB is rotating with a uniform angular velocity of 62.831 radians per second. If you read the problem statement, uh, the angular velocity is given but acceleration has not been mentioned. So the angular velocity is uniform and hence there won't be any angular acceleration. I mean this alpha term will be 0. So hence ATR alpha will be 0. So that's why the tangential acceleration of link AB is 0. Now for BP and slider P, we don't know angular acceleration of these two components, but we know the direction in which this angular tangential acceleration component acts. For BP it acts perpendicular to BP, and slider P, as it is moving on a horizontal plane, the acceleration should be also on the horizontal plane only, so it will be along horizontal line AP only. So this much data is sufficient to draw acceleration diagram, but before going to draw the acceleration diagram I need to fix the scale. If you see the values here, they are around 246 and 1973. So the scale which I have selected is, I will assume 1 centimeter is equal to 200 meter per second square. That means if I divide it by 200 it will come around uh, 10 point sorry, yeah, 9 point something, so 9.1 or uh, yes, 9.5 something it will come. So take that value and draw a line of 9.5 centimeter, and this line should be parallel to link AB. So this is A dash, which represents radial acceleration component of link AB, and it is parallel to AB and its length to the radius scale is 9.5. Next, the tangential acceleration of link AB is 0. That means I don't have to draw a line perpendicular to this because its magnitude is 0. That means A dash and B will coincide. The same point will be B also. Now for BP, I know the radial component 246.42, and this component acts along link BP, and reduce it to scale which we have, the answer will be around 1.2 centimeters. So draw a line of 1.2 centimeter parallel to link BP starting from point B. So this is the line parallel to BP. On that line, I have to show a line of length 1.25 centimeter. So that's what I have done. Now, for the remaining two, uh, slider P's angular acceleration is 0, and I have to show these two lines only now, and of which this one is perpendicular to BP. That means draw a line perpendicular to this vector, and this one is along AP. That means a horizontal direction. So that's what I have drawn. So this is a line which is perpendicular to vector or link BP, and the another one is a horizontal line which is parallel to AP, and the point of coincidence is nothing but the point which is common to these two, that is point P. So that's what I have shown. Now complete the acceleration polygon. So here is the completed acceleration polygon. This is the net resultant acceleration, I mean the summation of this tangential and radial acceleration both, and this is the acceleration of slider. So what has been asked in the problem statement is you need to find out the uh, angular acceleration of link BP, for which you need to calculate the tangential acceleration of link BP. That is, you measure the length of this one, the length of a t b dash p or b dash p vector, which comes around 6.9 centimeter, multiply it by the scale which we have, and the answer is 1380 meter per second square, which should be written here. So this value comes here, and using this we can calculate the value of alpha easily, and that's what is asked. You need to find out the angular acceleration of BP. So alpha BP will be equal to this value divided by the length of this connecting rod, which is 2, and the answer is 690 radians per second square. So that's what is the answer. And then next what we have to find out is for the point D, how much is the acceleration. That's what has been asked. So first locate that point. Again the same rule, BP upon BD should be also equal on this one, BP upon BD. So based on that theorem, you locate point D and draw a line joining AD and measure the length of this line. It comes around 8.8 centimeter. Multiply it by the scale which we have and get the answer. It comes around 1760 meter per second square. Then next what has been asked is the last question in the problem statement is you need to determine the rubbing velocity of each pin. So for that I had drawn this table. There are three pins A, B, P, and for pin A the ground link is fixed and hence omega 1 is 0. The second link is crank, which is more rotating with the angular velocity of 62.831 radians per second, and the diameter of that pin as it has been mentioned in the problem statement is 0.05 meter. So the rubbing velocity will come as 3.14 meter per second. Similarly for second link, the value of omega 1 is the value of angular rotation of crank, which is 62.831, and omega 2 is the angular velocity of this connecting rod, which is minus 11.1. Why? Because this is rotating in clockwise direction, crank is rotating in clockwise direction, and obviously connecting rod will go in anti-clockwise direction, so the direction is changed and the diameter is zero point zero 0.05. So here it is the summation of these two multiplied by diameter. So omega 1 minus into minus 11.1 multiplied by 0.05. So that's what gives the answer as 3.7 meter per second. For last one, P, the BP is rotating in anti-clockwise direction with angular velocity of minus 11.1 radians per second, and the slider is not rotating actually. The slider is moving horizontally only, so that's why omega 2 is 0 and diameter of the pin is 0.05, and the answer of for velocity of rubbing of point pin P is minus 0.55 meter per second. So these are the last uh, things which have been asked in the problem statement. You need to determine the velocity of rubbing for pin A, B, and P. And that's the end of this problem. And please remember that you may not get the same answer when you practice the same problem, but a nearby answer you may get, and that is also a right answer. The accuracy of the answers here depends on how much accurately you draw the configuration diagram, velocity diagram, and acceleration diagram. So little variation in the answer, you don't have to worry about it. So with this, we'll conclude the second session, and please note on this second practice problem. Please practice this problem. I have also mentioned the answers for this problem. Just check whether you are getting the right answers or not. So that's all about for this session. Thank you. Again, if you have any questions, mail us at the mentioned email IDs.